Hello. The call got connected. Yes, sir. Okay. Thank you, sir. One second.
Okay, take care. Thank you. Okay, so good morning, everyone. So sorry for the delay. It's out of my hand. I couldn't do anything for it. So today we're going to start chapter 10. Okay. So in chapter 9 we discussed columns under uniaxial load. You have a load, okay, compression load on a column, okay, and we saw the design equation. It's just one design equation. The load, the axial load, is distributed among the concrete and the steel, okay, and you have the factor of safety phi, which is 0.65 or 0.75. 0.75 when you have spiral stirrups, or 0.65 when you have regular ties. And there is the factor safety alpha to account for accidental eccentricity. Okay, if there is some eccentricity that you didn't, due to problems with construction, so you have this factor safety. Now, what if you have a bending moment on the column? Okay, a large bending moment on the column, a compression force and bending moment. How would you design this, and how we're having both together? Should like for bending moment, we discussed this in chapter 2, 3, 4, 5, right? And we discussed the columns when you have a compression force in chapter 9. Okay, should you design for bending moment separately and for axial force or compression force separately? What do you think about this? No, you cannot design, okay, for bending moment and for normal or axial force independently. Why?
They act together.
Shear act together with bending. When you have bending moment, you have shear. They come together, right? But the type of stresses, the bending moment gives you what? Gives you normal stresses, right? Compression and tension, okay? Shear forces gives you shear stresses, okay? So they are independent of each other. The type of stress you have for bending moment and for shear are different, okay? While for bending moment and compression forces or axial forces, they give you the same type of stresses. When you have a bending moment, you have compression. You remember when you have a bending moment like this, you have a beam and you apply some uniform load. The bending moment becomes like this. When you take a section in this beam, the stresses, you have compression on this side and you have tension on this side, right? So bending gives you compression and tension. Compression force gives you compression. So they are related to each other. You cannot design each one independently or design for each one independently. So now, let's see. When you have, both acting together, the bending moment and the compression force. So let's say this is a column, okay? There is a compression force P acting on this column, okay? If we have a bending moment acting along with this compression force M, okay, we can express this, okay? So here we have P and M, compression force and bending moment. We can express this as if we only have a compression force, but with some eccentricity E. Okay? So this is equivalent this case here, just translating P from the centroid to some distance E is equivalent to having P and M. Okay? Why? Because this M is going to be P multiplied by the eccentricity. Multiplying P by E will give you that magnitude of the moment. Okay? So if you want to find the eccentricity, E, it's M over or divided by P. Okay? So now, as you see here, this moment can be expressed in terms of this eccentricity. What's the eccentricity? The eccentricity is the distance where this axial force is applied to what? To the centroid, right? So now we need to define the centroid. What's the centroid? Okay, is it the regular centroid that you learned in the statics course? That you know about the centroid of the body? No. So here, E is the eccentricity, which is the distance from the axial force P, okay, to, instead of saying the centroid, we're going to actually define a new term here called the plastic centroid, to the plastic centroid. So now, what's the plastic centroid? What do I mean by the plastic centroid? Over here, this P is acting at the plastic centroid. If there is no moment, then this P, this axial force, will give you uniform strain. Okay? Uniform strain. So this is the definition of the plastic centroid. The plastic centroid is the point where if an axial or normal force is applied, uniform strain will be developed. Okay? That's the definition of the plastic centroid. Okay? Now, let's see what the cases where P and M, the combinations where P and M, okay, can result in. Okay? Let's take it from one extreme to the other extreme. Okay? So, cases of P and M. Let's start with P, the value of P and M equal to 0. That's the first extreme. Okay? When you have P and M, the first extreme is M being 0, and you have P. Okay? And then we're going to take it to the other extreme, okay, step by step, and see what happens. So when you have P, so this is the column, you only have P. Where's P? P is acting at the plastic centroid, okay? And there is no moment, so the eccentricity is 0. What's that case? This is the case that we studied in chapter 9. You only have an axial force. There is no bending stresses, okay? So when you have this, this is covered in chapter 9. And that means P is acting at the plastic centroid. Okay? And the strain distribution, if you draw the strain distribution at failure, this is the strain distribution at failure. When would the concrete fail? The concrete will fail when the strain is how much? 0.003. So the strain distribution at failure, it's uniform. You have uniform strain distribution. The strain everywhere is equal to the maximum strain that can be held by the concrete, which is 0.003. Okay? This is at failure. So that means that the stress is going to be constant in the concrete, is going to be 0.85 FC prime. That's what we had, okay? And the steel is going to yield, so the stress in the steel is going to be F yield, any steel that you have, okay? And you can find how much is P for this column, okay? That can be resisted by this column if only an axial force is applied, okay? Now, the second case, you have a P and you have small eccentricity or small moment. If the eccentricity is small, the moment is small, right? E is m divided by p, right? So now what do you have if it's the same column? This is the plastic centroid. Now P start to move from the plastic centroid with a small eccentricity, just small eccentricity. So at failure, what will happen if this is a very, very small eccentricity, okay? Now, we want to see what's the effect having a P and an M, right? This is equivalent to having, let me draw this here on that side. This is equivalent to having P right at the plastic centroid plus a moment, right? Adding those together, M and P, okay? It gives you a P that is, eccentric with the column, okay? Now, let's see the strain distribution. When you have a moment like this, what would the moment result in? Would you have a uniform strain distribution? What's the strain distribution? How does the strain distribution look like for a moment, when the moment is applied? Okay, we said the strain distribution is always linear, okay? So a moment like this, it will give you compression on this side and tension on this side, right? So the strain distribution is linear, it's not constant, and it's like this. So here this is compression, and here this is tension, okay? This is when you have, this is the strain distribution. When you have an axial force, how does the strain distribution look like? Only an axial force. How does the strain distribution look like? We just do this. Uniform or constant. Okay? It's all compression. You have a compression force. It's all compression strain. Okay? This is the strain distribution. So now when you have both applied together, a bending moment and an axial force, I need to add those strain distributions, okay? So how does the strain distribution look like? Here you have compression, and here you have compression at the same point. So the compression strain is going to increase, right? So you're going to have a higher strain or compression strain on this side. On the other side here, okay, you have here tensile strain, and here you have compression strain. So the resultant, what do you think? Will it be compression or tension? It depends on how large is the bending moment, right? If the bending moment, if this strain is larger than this strain, then it's going to be positive, right? If this negative strain or compression strain is larger than the tensile strain, it's going to remain negative, right? Our case here, we said we start with a small bending moment, okay? So small bending moment, okay? I mean here that this tensile strain is going to be small compared to the compression strain here. So the overall, it would remain negative here. But it's not going to be the same negative value here, right? This is large, very large negative strain. This is smaller negative strain here. So the strain at failure will look, or the strain will look like this. It's all compression, right? This is the strain distribution. At failure, when will this column fail? What do you think? When will this column? As you see here, this column, according to this strain distribution, it's all under compression, right? It's compression everywhere. But the compression here is smaller than the compression here. When will it fail? When this large compression strain reaches the ultimate value, right? So it will fail when this value here. So at failure, it will only fail when the strain here is equal to 0.003. Once the strain here reaches 0.003, it will fail. The column will fail, right? The concrete will crush and the column will fail, okay? Now, let's go ahead and increase the moment more. We started with 0 moment and we're increasing the moment, okay? Bit by bit. So we still have a compression force and larger moment, or E, larger moment or larger eccentricity. Both have the same meaning, okay? So now we still have the same column here. We have this P, but now the eccentricity is higher. We have higher eccentricity or larger eccentricity, okay? So this can be translated into the P, axial force that is acting at the centroid or the plastic centroid, to be more precise in wording, and a moment. Again, the moment will result in compression and tensile strain. The axial force will result in uniform strain. If you add them together, now the case, this is going to be negative over here, and those tensile strain and those compression strain, let's say at this case they are equal to each other. So again, the entire column is still under compression, but it's 0 at the end here. When will this column fail? When the concrete here crushes, okay? When the strain here is 0.003, okay? This is where this column is going to fail, okay? So as you see in each and every case here, the concrete or the column will fail when the concrete reaches 0.003 at some point, at the maximum point or the, the edge of the column. Now, let's take this, to a next step. P and larger moment. What will happen now? How will the strain distribution look like if I increase the moment more?
Positive.
Exactly. So the strain distribution, I'm not going to draw those again. Okay, strain distribution will look like this. You will start developing some tensile strain on one side of the column, and the other side of the column, it will have compression strain. You won't ever have tensile on both sides. You can have compression everywhere, but you cannot have tension everywhere, right? Why is this? Because I'm adding those together, right? So here you have negative and negative, so definitely negative plus negative is always negative. So you're always going to have negative on one side. It's the other side that we don't know what we're going to get. Will it be negative or positive, okay? So here, this column, when will it fail? What controls the failure of the column? Again, when this strain becomes 0.003. What about this strain? I don't care about this strain. Why? Because anyway, the concrete, we know the concrete is weak in tension, right? And that the concrete on this side, on the tensile side, will crack, will develop cracks, okay? And I will depend on the steel, on resisting the tensile force. I'm not depending on the concrete, right? We always depend on the steel in resisting the tensile force, not the concrete. I don't care about the concrete here. It will develop cracks and I'm not going to use it, okay? I'm using here the steel. And the steel, okay, it can, you know, the strain can go beyond yielding, right? And I can still depend on it. So actually what controls the failure of the column over here is the strain, the compression strain here. So again, it will fail when this is 0.003. Okay? In this case, let's say the strain here is, or where the steel is, epsilon s is less than epsilon u. Okay? But here, again, the column will fail. Okay? Even if the steel didn't yield, okay? The steel here, there is some tensile strain in the steel. It didn't yield, but the failure will happen due to the crushing of the concrete on the compression side. Okay? Now, a very important thing. When this column is going to fail, okay, the strain, the tensile strain in the steel is less than the epsilon yield. It's less than the yielding strain. Can you use such a column? You cannot use it as a beam, okay? So the ACI code prevents you, okay, to use a beam, okay, where the strain here in the steel is less than what? 0.004, right? You remember chapter 3 and 4, right? If the strain is less than 0.004, okay, you don't have enough warning, okay, you cannot use this. But this is only in beams. If you have a beam column, what's a beam column? A beam column is the column where you have compression force and a bending moment. If you have a beam column, no, that's fine. The compression strain, or sorry, the tensile strain can be any value, okay? But now, if the strain here is less than epsilon yield, phi is going to be 0.65. It acts as a column, okay? And phi is 0.65, okay? Now, let's go ahead, okay, and go beyond, increase the moment more and more, okay? So this is 5, P, and larger moment, okay? How does the strain distribution would look like? Again, here at failure, this is going to be 0.003, and epsilon steel here will just become larger than epsilon yield, okay? Now, how much is phi? Phi, once you reach this limit, okay, that epsilon steel, okay, is larger than epsilon yield. If epsilon steel is larger than epsilon yield, so how much is phi? Phi comes from the equation that we used for the beams, okay? What is that? Phi is 0.65 plus 0.25 multiplied by epsilon steel minus epsilon yield divided by 0.005 minus minus epsilon yield. What's this? This is the same equation we had for the beams, okay? But for the beams, we had a limitation for it. Epsilon steel cannot be less than 0.004, right? Here, epsilon steel can be less than 0.004 because you don't only have a moment. You have a moment and a compression force, okay? This is when you have regular ties. And it's like this, okay, when you have spiral stirrups, okay? And the value of phi here cannot be larger than 0.9. Okay? The maximum value of phi is 0.9. When would it be larger than 0.9? Can it be larger than 0.9 from the equation? If epsilon steel is larger than 0.005, then it's going to be larger than 0.9, but you know the limitation phi cannot be larger than 0.9. Okay, if epsilon steel is larger than 0.005, okay, then you just take it 0.9. Okay, then phi is 0.9. You don't go beyond 0.9. This is the equation, or this is, you know, if you remember that curve that we drew before, phi, epsilon, steel over here, this is 0.005, this is epsilon yield, so here we have 0.9, here we have 0.65, and then we have this curve, or this line in between. Okay? So the maximum value for phi is 0.9 when the strain is 0.005. For beams, we had a limitation here, 0.004. We cannot go in this range. But now, for beam columns, you can go everywhere. Okay? The strain in the steel can be any value. Okay? So this is the fifth case. Okay? What's the sixth? Okay? You keep increasing the moment. Nothing new is going to happen, right? You're still going to have compression strain on one side. If you increase the moment more, you're going to have compression strain on this side, and you're still going to have strain here that is larger than the yield strain. So increasing the moment, this is not a new case. So the other extreme now we reach is the other extreme is the moment is larger and larger, but P is smaller and smaller, it's 0. So you have M, okay, and P equal to 0. The moment is larger and larger, but the compression force is smaller. What's that case? What does this represent? This is a beam covered in chapters 3 to 5. Okay? This is not a new case, but this is the extreme case, okay, that you can have. So now, for those cases that we mentioned, those 6 cases, you start with P, okay, just P, and M, okay, and you manipulate those values, okay. How much is the maximum, if you have the same geometry, the same steel, okay, how much P and M can this column resist, okay? It depends on which case are you studying, okay? So now, let's say you have a column that is given, that is like this. Okay? So now, for a given column dimension, how much P and M can be resisted? What would we call this? B nominal. Okay? P nominal and M nominal. What's the nominal? Without factor of safety, okay? Can be resisted. Okay? So this will change from one case to another. So let's plot those together. This is a new curve that we first, we ever draw now, okay? P here, P nominal, and M nominal. the first case that we mentioned when we had a Pn only, a normal force, there is no moment, you can find the strength of that column according to what you learned in chapter 9, right? It's just P, right? How would you find P nominal? From the equation, right? So this is here in case 1. Let's go up here. In that case 1, okay? How much is P nominal? If you're given the dimensions of the column, the steel in the column, can you find the nominal strength of that column? What's the nominal strength of that column? According to what you learned in chapter 9. What's this? 0.85 FC prime area gross minus area steel plus F yield area steel. Right? This is the equation that we used, but we only multiplied this by 2 factor of safeties, right? Phi and alpha, right? But now this is the nominal strength when you only have a compression force. So you can calculate, okay, the strength of that column. There is no moment resisted here, only a normal force. So here, as you see at that point, this is point 1 here. You have an axial strength, but 0 moment strength. Okay? As you go to case 2, okay? So over here, case 2, okay? Where you have some bending moment and some P, the strain distribution will look like this, okay? We're going to learn how to find how much is M in P that will give us some strain distribution like this, okay? And then we're going to plot it. Find how much is P and M that give us this strain distribution, okay? It will be like this. So actually, for this column to start resisting some bending moment while there is an axial force, the axial strength is going to decrease to allow the column to be able to resist some bending moment. Okay? And then point 3 is going to be somewhere like this. Point 3 is where the strain on the other side of the column becomes 0. Right? And then we're going to have a point here. This is called the balanced point. What's the balanced point? The balanced point is where the strain in the steel is equal to epsilon yield. Okay? And then as the strain becomes on the tensile side increases and increases, okay? You're going to find this value here. What's this point here? You're going to have some value here. This is actually point 4 is here. And then this is 0.5. And then this is 0.6. Okay? Now, if I draw a curve connecting those values, this curve is called the interaction diagram. That gives me, points on that curve, gives me the strength of the column. Okay, how much P and M can be resisted, okay, together, okay, concurrently. You can be within that curve here. So if, let's say here, if you have a P and M over here, the column can resist them because it's within the limitation of that curve. Okay? But if you're outside that curve, the column will fail. Okay? So as long as you're inside that curve, you're good. Okay? Failure will not happen. Failure will happen when you reach that curve. Right? That curve, those points were at failure, right? So that's the interaction diagram. We're going to learn how to construct that interaction diagram. Okay? How would we construct that interaction diagram? We build it point by point. Okay? We just build it point by point. Actually, you know how to get 2 points on that curve right now. What are those 2 points that you know how to get on this curve?
6.
1 and 6. 1 is the case where you have just the column, just a normal force, there is no bending moment. And case 6 is when you have only moment, there is no axial force, no compression force, right? So case 6 is just a beam analysis, right? So you know how to get point 1 and 6. We're going to learn how to get, more points here. As you see, this curve, it's a curve, okay? It's not a straight line, but this part here from point 1 to the penance point is nearly linear, okay? So if you don't have time, you can just shoot for this point, okay? And draw a line in between here. And if you don't have enough time, the curve over here, you can neglect it and just draw a straight line like this, okay? So it's so easy to construct that curve. If you don't have time, if you don't want to have this curve in high accuracy, you can just get 1, 2, 3 points and then connect them together. Okay? So we're going to continue from here next time. I'm so sorry for starting late today, but as you see, it wasn't there was a technical problem that I couldn't solve it. So any question? Okay, so see you on Wednesday.